Okay. So, good morning. I will have to record this class today. There is a student that couldn't come, so I'm recording it so that the student can watch it later on. Okay, so the reason why I'm explaining that is because I will need to stay closer to my laptop. Okay, so I won't be moving so much. And if I do, please remind me, because sometimes I may forget it and then I'll be walking around. So don't let me forget that. Okay? Okay, so as you know, we're studying relations, right? And last class, you guys actually used one of the famous implementations of relations. And the reason why we implemented encryption was because encryption is a combination of functions, relations, that is leveraging all the different types of properties that we are going to see when it comes to relations. Okay? So stuff such as symmetry, directed graph, those are all concepts that we have in relations that are applied to cryptography. Okay? And today, I believe that we have enough time to take a look at that. We're also going to take a look at another resource, very common resource that we have in IT that also implements relations, which is relational databases. Okay? But before, although last class was a very hands-on class, very technical, now we have to go back to the concepts. And the idea here is to take a look, at least briefly understand some of those concepts that we have in relations. So, properties of relations. First of all, let's recap what a relation is. And a relation is nothing more than when you have two or more separate sets. Although you can also have relations in using one single set. We are actually going to take a look at that. Like I said, directed graph is something that you use when it comes to relations involving the same set. Okay, but we'll get there. But anyways, think of a situation where you have different sets and you want to establish a relation between those two or more different sets. How do you do that? You need to compute the Cartesian product between those two sets, right? And then the subsets of that Cartesian product, they are going to be somehow the result of the relations of those two sets. Okay. I like to expose these examples because they make it easier for us to understand all these different concepts, right? So let's take a look at what we have here. If we define a relation L from real numbers to real numbers, or if you prefer, if you want to verify if R is related to R by L. Two different ways of reading this, okay? But let's just follow what we have there. If I have a relation L from R to R as follows. So, for all real numbers X and Y, that's what we have, right? R to R, real to real. Where X is in the first, is in the domain R, and Y is also in the same domain R. But there is a function that establishes a condition for that relation. This is the first important factor here. A relation is established having a condition, okay? So there is a condition to define whether a subset or ordered pair or whatever that is is part of the relation between those two sets. What is the condition here? So X is related to Y by L, or relation L from X to Y, and then you have those arrows, right? You have this symbol here that represents the condition. If. So X is related to Y by L if X is less than Y. That's the condition. That's the conditional function. So if we look at those statements there, A, B, C, and D, which of them are accurate? Which of them are true? For example, A, is 57 related to 53 by L? The condition is X must be lesser than Y. Is 57 lesser than 53? B, is minus 17 lesser than minus 14? C, is 147 less than 143? Is 143 less than 143? It's equal, not less. And D, is minus 35 less than 1. So that's the function, right? It may be necessary, depending on the situation, or at least helpful, to draw a graph that represents the Cartesian plane. We're not going to worry about that right now, okay? That's not our concern right now. Okay, so as you can see, A, B, C, and D. Okay. If we take a look at another example here, define a relation E from Z to Z. What is that range of, that nature of numbers represented by Z? What type of numbers am I referring to? Naturals, integers, fractionals, reals. Those are the integers, right? The integers. So imagine a relation where you have integers and integers, the realm of all integers, and another realm of integers as well. Okay? For every ordered pair M and N in the Cartesian product of those integers, here's the condition. M is related to N by E if, that's our condition, M minus N is even. So the ordered pair, M and N, they will be related when M minus N is even. Now I ask you, when is that going to happen? When is M minus N be even?
When both M and N are even.
When they're both even, right? Correct? What else? When they're both odd. So both situations will give me an even number. Okay? So is 4 E0, is 2 E6, is 3 E minus 3. Well, I guess that you already get the point there. Those are all even, right? As they said, you have to either have both even or both odd. Okay. It also asks you to prove that n is an odd, and when n is an odd number, right? We don't have to go through that. It's not important for us. Proving the mathematical proof is not important for us. But there is something that I do want you to understand, because this is going to be important for our next steps. Because we're going to see that when it comes to relations, as you see there is a number of properties that are very important for us to achieve a solution or a result. Okay? Remember when we discussing functions, and I mentioned a bunch of properties of functions, and I told you, hey, we don't actually need to know these properties, but they are very, very helpful, because you can just jump ahead when you are solving a function problem. De Morgan's property, do you remember? Because this is, I'm mentioning De Morgan's property, this is because this is the one that I mentioned so many, many times, right? So what were all of those properties? Basically, it's a proof of when you have a specific situation, you can get to another point, right? And there is a proof to that. But the good thing here is that you can just move ahead. When you see this situation here, you can just jump ahead to that other situation there, that other function, that other model, okay? It's going to save you time. It's the same thing here. So, what are we looking at here? Do you agree with me? Let's see if you agree with me. Do you agree with me if I tell you that you don't really need to make any kind of mathematical computation to tell whether those two different numbers are both odd numbers or whether they're both even numbers? You don't have to do any math to tell that, do you? You don't. 17 and 123. Okay. I know, right? They're both odd numbers. But there is a mathematical proof to that. How do I verify if a number is even or odd, mathematically speaking?
See if it's divisible by 2 without a remainder.
Yes, exactly. Right? Which is, you compute the modulo, right? Divide by 2, if the remainder is 0, that's even. If it's 1, odd, right? Very good. Now, this is one possible mathematical model to verify if a number is, if two numbers are odd or not. Okay? So, n equals 2k plus 1, that is one way of verifying that. Just keep that in mind, because we're going to go back to that eventually. Okay? Now, when you have two values, that the modulo, okay, of those two values the modulo 2, module with base 2, modulo 2 of those two values is the same, which means that the remainder is the same, you're going to say that those two values are congruent modulo 2. So basically, we were talking about even and odd numbers. If I have two values that are even, they are congruent modulo 2. If I have two values that are odd, they are also congruent modulo 2. And I know it may sound stupid because, well, why would we use this type of nomenclature, this taxonomy, congruent modulo 2, if we can simply say even or odd, right? And you're right. Seems like it doesn't make sense. But just keep this in mind because we're also going to look at congruent modulo n. Which is something that was applied to the secret key encryption that we used here in class. Remember the Caesar cipher. It uses the idea of a congruent modulo n, which is, if I have two different values, but modulo n of those two different values is the same, then I'm going to say that they are congruent modulo n. What is the situation? Let's take a look at an example. If you pick two random values, two random numbers, divide those random numbers by what? 5, for example. Okay? If the remainder is the same, we're going to say that they are congruent modulo 5. Again, an example. 26 and 51. Are they congruent modulo 5? 26 divided by 5. What's the remainder? 1. What's the other number that I've said? 51. 51 divided by 5. What's the remainder? 1 as well. Are they both congruent modulo 5? Yes, they are. Okay? So these are just some properties that we have when it comes to relations. Okay? Again, just try to keep these, let's say, these properties, the properties names, in mind, because when we get to understanding relational databases, and then understanding cryptography, this is going to be very, very helpful. Okay? We also have the concept of a relation on a power set. Obviously, we need to recap what a power set is. Do you remember what that is?
The set of all subsets?
The set of all subsets. Very good, Stefan. Yes. So, for example, if we consider here our set X, what's the power of X? It's the combination, the subsets of the set, or the superset if you prefer, right? So you have the empty set, you have set with the only one element of the superset, so with A, then another one only with the element B, another one with the element C. Then I start I do all types of combinations, right? So I'll have AB, AC, BC, and then all three ABC, right? That's what a power set is. Okay, we know what a power set is. Now, define a relation S from Px power set of X to power set of X, okay? As follows. For all sets A and B in the power set of X, there it is. This is how you express a relation between subsets of a power set. So, relation S from A to B, and then comes our condition. If A has at least as many elements as B. Okay? So we're not considering independent values, are we? Independent elements. We're considering subsets. So at first, we were analyzing relations, considering elements of sets or subsets. Now we're talking about relations that consider subsets of sets, not specific elements, right? Then we also have the inverse of a relation, which we talked about, okay? The idea here is pretty simple. But let's also consider the arrow diagram for inverse relations. So if I have R, which is a relation from A to B, then a relation, the inverse relation, okay? Relation R minus 1, that's the inverse relation, okay? The inverse of a relation R from B to A, because it's inverted, can be defined by interchanging the elements of all the ordered pairs of R. Okay. Let's try to better understand that. Consider those two sets. A with elements 2, 3, 4, and B with elements 2, 6, 5. And let R be the divides relation from A to B for every ordered pair X and Y in the Cartesian product between A and B. So, in summary, what we have here is relation R from X to Y if, and that's our conditional function, if this symbol here, guys, okay, the pipe, it represents divides. The first element or variable, okay, divides the second one. So the condition is X must divide Y. Okay? What are the examples that we have here? A has 2, 3, 4. B has 2, 6, 8. What elements of A divides elements of B? So I can build those ordered pairs. Look. Let's first consider the first element of A. For the first element of A, 2, number 2, what elements of B does 2 divide? 2 divides what elements of B? 2, 6, and 8. Good. Let's go to the next one. 3. 3 divides what elements of B? 6. And then finally 4, which divides? 8. Right? So look, the first thing that is important to observe here, we saw that a relation initially, a relation is what? The Cartesian product between the involved sets. Right? Is this R? Is R the pure Cartesian product between sets A and B? Let me ask you again. Is the relation R that we see here as a result the pure Cartesian product between A and B? It's not, right? Why not, David? What's different?
For it to be the Cartesian product, then you would have to have an ordered pair for each of the domain equilibrium.
So David said, well, the Cartesian product between A and B would be the product between the definition of the ordered pairs or all ordered pairs for each element of A related to each element of B, which would be 2, 2, 2, 6, 2, 8, 3, 2, 3, 6, 3, 8, 4, 2, 4, 6, 4, 8. That would be the Cartesian product. Why is the relation here not that simple Cartesian product? Why not? Because of the condition, right? So a relation is not only, could be simply the Cartesian product between the involved sets. If there is no condition, we're now establishing relations where you have conditions. You have conditional statements. So it's not only the Cartesian product, that as well, but once you get the Cartesian product, you also need to analyze the condition. And according to that condition, that would be the relation R from A to B if X divides Y. Does that make sense? Yes. So, we saw at first that the relation is the Cartesian product between the involved sets, right? Which would result in many more ordered pairs than what we see there. Why is that? Because there are situations where a relation between two sets or two functions, okay, can be simply the Cartesian product. But you may have conditional statements as well. You may have conditions to make that relation an actual relation between the involved pair, the involved sets. Okay. Is there a condition here? Yes. Yes. The condition is the ordered pair X and Y, which you read the relation from X to Y, or X is related to Y by R. Really doesn't matter, you can read it both ways. So there is a condition, okay? There is a condition. And what is the conditional function? X divides Y. So, are X and Y related? Yes, if X divides Y. That's the condition. Okay? And that's how we got to that. Because these are the only ordered pairs, right? If you build that entire Cartesian product, 2, 2, 2, 6, 2, 8, 3, 2, 3, 6, 3, 8, 4, 2, 4, 6, 4, 8. Out of all of those pairs, these are the only ones that suffice that condition. X divides y. Therefore, the relation set is this. Agreed? Okay. Now, we're analyzing the inverse of a relation. And what is the inverse of a relation? You reverse the ordered pairs if the relation is composed of the direct relation, not the inverse relation. If the direct relation is composed of ordered pairs, you simply invert the ordered pairs. That's the result. 2, 2, 6, 2, 8, 2, so forth, so on. Okay? Now, if you try to correlate these properties that we are studying with what we talked about last class regarding encryption, cryptography, you're going to see that you apply all of these properties there. Look, do you agree if I tell you that the inverse of a relation is simply after computing the Cartesian product, considering the conditional function, right? But anyways, if you have the Cartesian product, you can get back to the source, to the origin, if you have the result. Look, if this is the Cartesian product, and considering that the codomain is the result or the output, if I inverse this, I get back to my source. Does that make sense? Right? Obviously, it's not that simple when you're applying it, because there's going to be a lot of functions involved. But the idea is, I have X, my source, my input, right? And applied to a function, I'm going to have my output, my Y, my result. But if I get the result and I invert the function, and that's what I'm inverting. If I invert the function, I go back to my source, to my input, to my original values. Right? Cryptography, the shared key cryptography, the secret key cryptography, Caesar cipher, for example. That's exactly what that was, wasn't it? Right? If I have a letter, I dislocate that letter 3 positions to the right. I advance 3 positions. How do I decrypt it? I go back. But there is a function, and you need to invert that function. Well, if what I'm saying is true, consider that, and considering that the relation R from X to Y is conditioned by the function X divides Y. If I have Y, how do I get to X? X must be multiple of y must be multiple of x. That's the inverse, isn't it? So, first of all, in a diagram, that's how you represent the relation, and you have two different ways of representing the inverse of a relation. You either invert the arrows, or you put B, if you have sets A and B comes first, A becomes the output, becomes the result. Okay, so just two different ways of doing the representing using the arrow diagram. Okay. So, the inverse of relation R can be described in words as follows. For every ordered pair y and x, because it's inverted, in B Cartesian product A, bless you, the inverse of relation R from y to x if y is a multiple of x. So we're basically inverting everything, right? Another example that is not important for us. Okay, another concept that we need to understand, another property that we need to understand. Directed graph of a relation. A relationally set A is a relation from A to A. What's different here? Just by looking at this, is it any different from what we've seen so far as relations? Very good. There is only one set, right? There is only one set. So, a relation on a set A in one single set is a relation from A to A. There are situations where you may have subsets that are the result, the Cartesian product, or the relation with itself. No problem there, right? For example, we analyzed that before. The set of all integer values, all z's, z to z. Okay? So that's possible. You understand why this is important, okay? So you're considering that you have only one set. A relation on a set A is a relation from A to A. You have a relation involving the same set. When a relation R is defined on a set A, the arrow diagram of the relation can be modified so that it becomes a directed graph. Okay? That's what a directed graph is. Instead of representing A as two separate sets of points, represent A only once and draw an arrow from each point of A to each related point. As with an ordinary arrow diagram, for all points x and y in A, there is an arrow from x to y if the relation R from x to y if the ordered pair x, y is in R. Okay, again, let's look at an example here to better understand what we're doing. So consider this set. Set A composed of the elements 3, 4, 5, 6, and 7, and define the relation R on A as follows. For every ordered pair, X and Y, in A, you have that pair if, you have that pair in the relation if 2 divides X minus Y. Okay, so what's our condition here? 2 divides X minus Y. Tell me something. What function is that? 2 divides X minus Y. Two divides says that it's what? X minus Y must be modulo 2. Right? And if the difference between X minus Y must be modulo 2, I have that same idea, the congruent modulo 2. Right? Does it make sense? Let's see, let's take a look at a few examples, a few possible values here. So, again, A, 3, 4, 5, 6, 7, 8. If we consider that X is 3, it's an element of A, and Y is 3 as well, also an element of A, right? Are they related? Well, let's see. If we do X minus Y, 3 minus 3, that's 0. Does 2 divide 0? You can't divide 2 by 0, but you can divide 0 by 2, right? So 2 divides 0 is 0 divided by 2. Am I right? So, since 2 divides 0, the condition here, is attended, right? Okay. So the ordered pair 3, 3 will be part of the directed graph. You have one single set, 2 elements of that single set that are respecting the conditional statement for that relation. If we consider, for example, a situation where Y is greater than X, such as 3 and 5. 3 minus 5, that's minus 2. Does 2 divide minus 2? Yes, it does. So, as a result, this is a directed graph that you're going to get. If we are comparing that with this, for example, It's the same idea, right? I have an arrow diagram, but traditionally or most commonly, you're going to use an arrow diagram to establish the relation between source and destination, right? X and Y. Why can't you use X and Y being elements of the same set? There's no problem there. No problem at all. Okay? The only difference is that the arrow diagram will be composed of what is called a directed graph. Because you have only one set. The elements are all here. And then you use the, you build the arrow diagram. In this example, that's the result you're going to get. I don't know if at some point during the course you're doing your program, you're going to study Markov chains. Okay? Markov chains is a more complex implementation of this. Directed graphs combined with the traditional relations involving more than two sets. So you have this combined with this. Actually, a bunch of these. Okay? So just another definition here that we need to understand. This is going to be brief, okay? So we have 2 minutes. That's more than enough. So we've been talking about all of these properties, right? Properties of relations. And again, I like to give examples, especially if I can give you realistic examples of, or examples that are applicable to what you guys are going to do or what you're studying. So I mentioned relational databases several times. A special group of relations called N-ary relations from the mathematical foundation for relational database theory. So basically, relational databases are built, the idea of a relational database is built on this type of relation, okay? Which can create a N-ary relation or N-ary relations. So let's understand what that is. Just as a binary relation is a subset of a Cartesian product of two sets, so we saw a directed graph, which is relations of single sets. We also looked at relations between two sets, but we have relations between among more than two sets. So just as binary relation is a subset of a Cartesian product of two sets, and N-ary relation is a subset of a Cartesian product of n sets. Okay? So if you have several sets here, let's analyze the situation where you have 4 sets. First of all, binary, when you have 2 sets, ternary, quaternary relations, right? Okay, so the following is a radically simplified version of a database that might be used in a hospital. Let's say that in that hospital you have a set A1 to be a set of positive integers. A2 is a set of alphabetic character strings. A3, a set of numerical character strings. A4, a set of alphabetic character strings. Define a quaternary relation R on the Cartesian product among A1, A2, and A3 and A4 as follows. Well, first of all, it's a quaternary relation because it's relating 4 sets. And if you recollect, if we go back, we're going to remember that when we have a Cartesian product, the ordered tuples, I'm not saying ordered pairs, the ordered tuples, the number of elements of a ordered tuple will depend on the number of sets. What I'm saying is, how many sets do I have here? 4. If I have 4 sets, the Cartesian product of those 4 sets will result in ordered 4 tuples, not ordered pairs, not ordered triples, 4 tuples. 1 element of each of those sets. Right? Now, if we consider that the elements of set 1 is going to be the patient ID, the elements of set 2 is going to be the patient's name, the elements of set 3 is going to be the date of admission, and the elements of set 4 is going to be a primary diagnosis. This is an example of several tuples, actually. Okay? This is what a relational database does. That's all that is. I have one table with the patient IDs. I have another table with the patient's names. I have another table with the date of admission of my patients. And I have another table with their diagnosis. 4 separate tables. How do I correlate those tables? How do I correlate the records of those tables? Cartesian products. And then I apply filters to find the specific records, the specific entries that I want. So for example, if I want to find all my patients that were admitted on January 3rd, 2019, this is what I do, and that's what I'm going to get. Oops, I'm sorry. Oh, wait. Yeah. Although I'm only listing the patient ID and the name, okay? But I'm using the admission date to find the records that I want. So, if I'm looking for, if I'm looking for my patients that were admitted on 01/03/19, this is what I should get. This one and this one. Sarah and John. Oh, I'm sorry. Sarah and Mary. Right? So again, database is the exact implementation of Cartesian products, establishing relations between sets. In this case, what are the sets? They are nothing more than tables records. That's all that is. Okay? It took a little bit longer than 2 minutes, but you get the point. Any questions? Okay, thank you guys. I'll see you on Friday. On Friday we'll continue our properties of relations. towards understanding cryptography.
What do we?
You too. Yeah.